Okay, we've just said that integration is too horrible to even contemplate doing. I asked the class, well, how do you think you do it? Someone said, stick it in your calculator, and I said, if you've got a graphics calculator, yes, you can. Then I asked, thinking back to what else we've done so far in S2, what have we done? And people said we've used tables. In your tables, if you find page 19, you see this, the normal distribution function. Now on here, it doesn't give you a choice of mu, and it doesn't give you a choice of sigma. There aren't pages and pages of tables for different values of mu and different values of sigma. For the Poisson, there were tables for different values of lambda. They took up pages in the book. But here for the normal, you've just got one page of tables. And what we do is we convert every problem to have the same mean and the same standard deviation, and then we work on that converted problem. So what we had here in this example was our question said x was normally distributed 175 6 squared. We now do a conversion process which changes that to a normal distribution with a mean of, and if you look at the table in front of you, you'll probably work it out, with a mean of 0 and a standard deviation doesn't actually say on that page. Greg? It's another very basic number. 1. Yes. Okay. So we convert every problem from its original mu and sigma to be a new problem with a mean of 0 and a standard deviation of 1. And instead of being x or whatever we called it up here, this is called z.
How'd you get mean of 0?
Just the region on the side of an axis as well.
That would be correct, yes. So this one up here would have been centred on 175.
Yeah.
This one down here will be centred on 0. That was an x scale. This is a z scale. It will be centred on 0, that's correct. What do we do to x to make it into z? That is the key thing. There's a hint in that very horrible formula we wrote down at the beginning, in the thing that's a power on the e. What was...
You meant that equals something.
Oh, well, can't we shift it down?
You shift it down.
That way x minus the standard deviation. No.
It's not minus the standard deviation.
Minus the mean.
Minus the mean, yeah. If I took 175 off every value there, that curve would just slide left, and then its mirror line wouldn't be above 175, but would be above 0. So z, first thing we do from our x is we take away the mean value. That purely slides everything down the number line. So now it's not centred above 175, but that has fixed it to be centred above 0. The next bit, the standard deviation bit, this fixes its shape to be consistently wide or narrow, if that makes sense. But it fixes it. Then we now divide that sigma. And that is your next red box rule. Z is x minus mu over sigma.
Is that the capital X?
In this case it is, but normally after this case actually it will be, we'll pretty much always use a lowercase. Okay. But z is a continuous random variable in its own right, so I could use an uppercase one there.
What's happened?
I took a bit of paper off.
No, I didn't really follow through on that.
Okay. We do this magic thing here.
Yeah.
Whatever our original distribution was,
Yeah.
from every x value I subtract the mean, and when I've done that I divide by the standard deviation, and that changes it from that distribution to this distribution. And this distribution here is the one whose probabilities are here. So once you've done that, you can use this, and that z there is basically the value you get when you do this transformation here. So if we keep going with this, find the probability somebody is smaller than Alex, I'm just going to write it all down again. Well, not write it all down again, just write down the basics here again. We had this distribution, and we were asked to find the probability that somebody was smaller than Alex. That's our distribution, that's our question. What we do is we change that value there, which is a specific value of x, so that's a little x value. We need to change that question into a probability that z is less than some specific z value. So that's an uppercase z, that's a lowercase z. So we need to work out what this z value is using this transformation that we've got here. Well, in this case, z will be the x value we had for Alex's height, take away the mean height of all the boys in year 13, divided by the standard deviation of all the boys in year 13.
So you want to find z?
Sorry?
1.5 z. What are you putting in 1.5? Is that an x?
Here,
No, you put an arrow.
There.
What's that?
that's a little x. That's a specific value that big X took there. So, if you work this out, what is z? As a number, as a decimal number, it's actually more helpful. I'm sure you can convert it into a decimal.
It's 10 over 3.
10 over 3. So that means, and I'm going to draw two diagrams now just to really sort of emphasise this point. I'm going to draw two diagrams, one under another. One is an X diagram, one is a Z diagram. Originally, I was dealing with a mean of 175, and I wanted to know about 195, and I wanted to know that area there. I converted this into a Z diagram with a mean of 0, and actually I'm now interested in, and if these were drawn properly, that would sort of be underneath it, I'm interested in 10 over 3, which is 3.33. So I'm now interested in, on this new curve, this area here, and those areas are the same. And now what I do is I look in my tables and I find 3.33 in my tables, except 3.33 is actually off the scale. Yes?
Well, you just round 3.33 or 3.33 per.
The tables only go to so many decimal places, as we'll see. Okay, actually I could go to 3 decimal places there. Okay? Right, if you look at the tables, the Z values go down the side here. Either Alex was so tall, or I just completely underestimated the average height of the year 13 boys and forgot to correct that this year. That actually 3.3 is off the scale down here. Okay? So, can we just pretend that the great god of statistics has made his only ever mistake, and the average height of boys in year 13 is not 175 centimetres? Can we make it 185, yes. Okay. So, let's just pretend a minute just to make this work. I ought to have made a note of this, so this didn't work last year. Okay? So, what we're doing now is we're changing mu. You can't really do this normally. Okay? Because the great god of statistics got it wrong. And we will say actually that mu was 185. remembered not to use that example next year. What calculation will I do then to get Z? Now I'm still dealing with Alex. Alex is still 195 centimetres tall. Was Alex really 195 centimetres tall? Maybe he was. So, what calculation will I do for Z? I will do the person's height, take away the mean, divided by the standard deviation. What does that come out to be this time? Yes, that's exactly right. What is that? 1.6 recurring, yeah. So if we do it to 1.667, if you do it 3 decimal places, that's accurate enough. I'm just going to stop here because I'm running out of time in this video.